Good morning, dear students. Welcome to the next part of the spectroscopy. Now we are familiar with this wonderful technique used for the identification and analyzing the compound as it deals with the study of the interaction of electromagnetic radiation in electromagnetic spectrum with the matter composed of atoms and the molecules. And the instrument which is used to analyze this interaction or the study is called spectrophotometer. The different parts of the spectrophotometer are the light source, monochromator, the sample holder, detector, amplifier, and recorder. Now we continue with the various types of the spectrophotometer in the lecture as well as the various types of the absorption spectroscopy. Following content should be covered in the lecture: the various types of the spectrophotometer or spectrometer, the types of the absorption spectroscopy, the UV visible spectroscopy, what is the principle of the UV visible spectroscopy, the different terms involved in the UV visible spectroscopy, and the absorption and intensity shifts found in the UV visible spectroscopy. What will be the learning outcome after this lecture? The student will be able to understand about different types of the spectrophotometer involved in the analysis, the types of the absorption spectroscopy in which the UV visible spectroscopy principle, the terms involved in the UV visible spectroscopy, and the absorption intensity shifts. So as we learn about the spectrophotometer, it consists of the various features having the light source, monochromator, sample holder, which is made up of a specific material on the basis of the electromagnetic radiation we are using for the interaction with the matter. Like in UV visible spectroscopy, the sample material is quartz, which do not absorb the UV visible range of the radiation. And if we talk about for the IR, the sample material should be of plastic or the glass. Then the detector, which plays an important role in the instrument, which converts the radiation of the energy into the signals. So now let's see the different types of the spectrophotometer used in the study of the spectroscopy. We can classify the instrument spectrophotometer into two types. The one is single beam spectrophotometer or single beam spectrometer, and the another one is double beam spectrophotometer. In single beam spectrometer, it is used to measure the intensity of the incident light, and the sample must be removed so that the reference can be placed each time. So once you have to place the sample and that analysis is recorded in the computer, now you have to remove the sample and put the reference in place of the sample and study out the difference so that your accurate results come up. And each time you have to do in this experiment, you have once at a time, you have either sample or the reference cell to be analyzed by this instrument. This type of the spectrometer is usually less expensive and less complicated. So you place one sample and then you can remove it with the reference, and then you can analyze your compound. But it is time consuming. The next spectrophotometer is the double beam spectrophotometer. In this type, before it reaches the sample, the light source is split into two separate beams. And from these, one passes through the sample and the second one is used for the reference. So as the monochromator converts the polychromatic radiation into the monochromatic radiation and allow to pass the monochromatic radiation to the sample, there only there is a device which split this beam of the radiation into two equal halves. You are able to see here we are having this beam which divides into two equal halves, and one is going to pass with the sample holder, sample cell, and the another one is passed through the reference cell. So we can simultaneously analyze both the reference as well as the sample, and here is the detector. So after the radiation, after passing through the sample and the reference cell, reaches to the detector, and detector converts that radiation into the signal which amplify and recorded in the unit. It is less time consuming, and this gives an advantage because the reference reading and the sample reading can take place at the same time, and you can have your output and you can easily analyze your sample. So double beam spectrophotometer has the advantage over the single beam spectrophotometer. Even the single beam spectrophotometer is less expensive, but it is time consuming. But double beam spectrophotometer, within a few time you can have your results simultaneously of the sample and the reference cell. So based on the wavelength of the radiation or the light source used in the spectrophotometer, we can also classify the spectrophotometer into different types. We have seen the single beam and double beam spectrophotometer has the different working. Now on the basis of the light source we use in the instrument, the different type of the spectrometer are there. The one is visible spectrometer, in which the light source is visible range of the radiation, that is 400 to 700 nanometers of the electromagnetic radiation, and we study out in this visible range of the radiation, and we have the normal spectrum. Get the visible spectrophotometer vary in accuracy. The plastic and the glass cuvette can be used for the visible light spectroscopy. So as we are talking about the sample holder or the material in which we put our sample or the cuvette, that is made up of glass or the plastic in visible range of the radiation. So this kind of the spectrophotometer is specific for the visible source, and the cuvette is also specific, that is of plastic or the glass. The second spectrometer is UV, and it uses the light over the UV range, and that is 180 to 400 nanometers. The ultraviolet spectroscopy is used for the fluids and even solids. The cuvettes made up of quartz are used for placing the sample. If we are using the double beam spectrophotometer, the sample material and the reference material both are made up of same material as a quartz. So UV, having the light source UV range of the radiation, that is specific 180 to 400 nanometers, and the material is made up of quartz. The third one is IR spectrophotometer, and it uses the IR range of the radiation. What is the IR range of the radiation? It is 700 to 15,000 of the electromagnetic radiation spectra. And again, if we talk about the cuvette, which is made up of an IR spectrophotometer, that is also of glass and the plastic like visible. So that is on the basis of the light source. The materials in which we put our sample, that also differs. So on the basis of that, the spectrophotometer are again classified into visible, ultraviolet, IR. We have read the absorption and the emission spectroscopy. It is easier to study out the absorption spectroscopy as compared to the emission spectroscopy. So on the basis of the studying of the absorption spectroscopy, we can categorize different type of this absorption spectroscopy. The one is the UV visible spectroscopy, that is also called the electronic spectroscopy. The another one is IR spectroscopy, which is also called vibrational spectroscopy. The third one is the microwave spectroscopy, which is also called the rotational spectroscopy. Then the nuclear magnetic resonance spectroscopy, that is NMR. So there are various kinds of the absorption spectroscopy on the basis of the radiation which we are focusing or interacting with the sample, and seeing the absorption spectra. Before we move towards the various types of the absorption spectroscopy, we should know the energy associated in a molecule. The total energy in a molecule is the sum of the energy EE, that is electronic energy, vibrational energy, rotational energy, that is ER. One more energy is there. We do not count that energy in the total energy because the energy is very small, which is taken negligible in the studying of the spectroscopy, that is ET. ET is the translational energy, which is there in a molecule, a small change in the position. So that translational energy is taken to be negligible in the study of the spectroscopy. That's why the total energy of a molecule is the sum of electronic energy, vibrational energy, EV, and rotational energy. The electronic energy is greater than the vibrational energy, and vibrational energy is greater than rotational energy. So here are the energy level you can understand here. We have the ground energy level, that is E0, that is the electronic ground state. E0, that is the lower energy state of the electron, and here is the next level, that is E1, and the more E2, E3, the electronic excited states are there. So E0, the electronic ground state, and E1. So you are able to see a large difference in this electronic energy level is there. That's why the electronic energy is very high energy required for an electron to jump from the lower state to the excited state. And that energy, it's the combined energy that is visible and the ultraviolet range of the energy, which is having this much of the energy which can jump the electron from the lower state to the ground state. This is. Now vibrational energy is less than the electronic energy. So in the electronic level only we have the vibrational levels. So here you are able to see the vibrational levels V1, V2, V3, V4. Understood? And here also in the excited state we have several vibrational levels are there. V1, V2 and V3. So the vibrational energy is less than the electronic energy. And the rotational energy is even lesser than vibrational. So in a single vibration we have many rotational that can be represented as J. The rotational level. In each one of the vibrational level there are many rotational levels. In that also the transitions occur when the energy is absorbed by the molecule. So that is represented by J. So J can be 1, 2, 3, several rotational levels are there within the vibrational levels. Here also. So many of the rotational levels are there in the vibrational levels. When a lesser amount of the energy is given, only the rotation is going to take place, and if higher amount of the energy is given, vibration also occur, including the rotation. When vibration occur, it includes the rotation because rotation energy is lesser. And if we talk about the electronic transition, if the electron jump from the ground state to the excited state, it undergo vibration also, it undergo rotation also. Understood? So the vibration and the rotation also causes when the electronic transitions occur. So that is very important here. The electronic energy is very high energy, vibrational energy and rotational energy. So always for the electronic transition we have the higher energy radiation required. When we give the sample the UV visible range of the radiation, then only the electronic transition takes place. This high energy transition takes place. If we give the lesser energy like IR, infrared radiation, it causes vibration. And if we give more lesser energy, that is microwave radiation, if you give, it only cause the rotation because it is lesser energy. So according to the energy given which is absorbed by the molecule, under these levels the transition takes place, and on the basis of that the molecule give the spectra. So as we understood the various energies associated in a molecule, now we see the one of the important type of the spectroscopy is UV visible spectroscopy. The ultraviolet visible absorption spectroscopy is the measurement of the attenuation of a beam of the light after it passes through the sample or after reflection from a sample surface. The absorption measurements can be at a single wavelength or over an extended spectral range. So when UV visible range of the radiation is passed through the sample, then after that the beam of the light is detected and recorded, in which we study out the absorption spectra. What is the principle of the UV visible spectroscopy? It involves the transition of an electron within a molecule or an ion from the lower energy state to the higher energy state or vice versa by the absorption or the emission of the radiation falling in UV visible range of the electromagnetic spectra. So when we interact the UV visible range of the radiation to the sample, in the sample, the transition of an electron takes place from low energy level to the high energy level. And this is the high energy radiations. When given to the molecule, then the electronic transitions occur, and by the absorption of this range of the radiation or by the emission of this radiation can go for studying the emission spectra. So that's the meaning of the vice versa. So this is the main principle involved here, and you know the UV range of the radiation, that is 15 to 400 nanometers, and for the visible range we have studied 400 to 700 nanometers. So it allows the electronic transitions to occur from low level to the high level. On the basis of that, the absorption spectra or the emission spectra can be studied. Why we use UV spectroscopy? It is very useful spectroscopy if we give this high energy radiations. It is very useful for the detection of the functional group present in the molecule. So each one of the functional group is having its own wavelength of the radiation absorbed in UV and visible range of the radiation. It can detect the impurities. We can easily detect the impurities by comparing the spectra with the standard spectra or the pure spectra. So we can easily identify the impurities. It can go for the qualitative analysis for identifying the groups present in the sample. The quantitative analysis by just calculating the area of the peak we are getting in the spectra. We have the quantitative analysis also. The single compound without the chromophore can be identified in this UV spectroscopy. The chromophore term which is used in the UV visible spectroscopy, we will read out. The drugs with the chromophoric reagent can also be determined in this spectroscopy. It also helps to show the relationship between different groups. It is useful to detect the conjugation. This is very important why we are going to study UV visible. So to detect the conjugation, we can easily find out the in the spectra the conjugation of the compounds. So here in this electromagnetic spectrum lying the UV visible range of the radiation, here you can easily understand the range, the region beyond the red we have infrared. So that is the infrared, and while that beyond the violet we have the ultraviolet. So the wavelength of the range of the UV radiations, it is in Armstrong as well as in nanometers. Mainly it is used at the blue end of the visible light, that is 4000 Armstrong, and ends at 2000 Armstrong. So that is in the Armstrong, you can able to have the range in nanometers, which is UV 15 to 400 nanometers and 400 to 700 nanometers. That's the visible range. To understand it in the electromagnetic spectra, we are give to have that basic idea of the UV visible radiation from the electromagnetic spectra, which is used in the analysis. So now we are going to various terms involved in studying the UV visible spectroscopy. The one of the important term which is used in the analysis, that is chromophore. And the Greek word, it is the meaning of this word is chrome means color and the phore means bearer. So it can be easily defined as any of the isolated covalently bonded group that shows the characteristic absorption of the electromagnetic radiation in UV or visible region. So chrome means color, and you only say that the colors which are visible to us, that groups can be the chromophore, but we can say it's a broad definition where the visible radiation or the ultraviolet radiation, it shows the absorption. Those groups are considered as the chromophore. Any isolated covalently bonded group which shows the absorption in this range, UV or visible range of the radiation, that is called a chromophore. Here you can have the compound containing the chromophore is also called chromogen. So we have ethylene group, C double bond C, carbonyl group, C double bond O, NO2 group. These all are the chromophores, means they absorb the UV or visible range of the radiation, and these groups are mainly analyzed by the UV visible spectroscopy, and the compound which contain this group, that chromogen, can be analyzed. The different types of the chromophore are there. The one is independent chromophores. If one chromophore is required to impart color, means only one group which is responsible for imparting the color of the compound, like azo group. It is the independent chromophore. Nitroso group, which is NO, it is also an independent chromophore. And dependent chromophores are those chromophores if more than one chromophore is required to impart the color. So the color of the compound is due to the presence of more than one chromophore which is responsible for imparting the color. That is called dependent chromophores. For example, the acetone having one ketonic group is colorless, whereas diacetyl having two ketonic group is yellow. So more than the groups should be more than one. If these are responsible for imparting color, acetone is only having one ketonic group responsible not for the color. But if we have two ketonic groups, it is making the color to the compound. So that's the difference between independent and the dependent chromophores. So here you are able to see in the table we have the various chromophore groups, and which is having a characteristic absorption in the UV visible range of the radiation. We have this carbon-carbon single bond, then double bond. It is also having the absorption in UV visible range of the radiation. We have seen this carbonyl group, it shows the having two type of the lambda max, maximum absorption of the wavelength which is absorbed here. It is showing then alcoholic group, and nitro group, which is a chromophore, and phenyl group, it is also showing the absorption to this characteristic lambda max. So maximum wavelength of the radiation which is absorbed in the category of the UV visible range of the radiation. So these all are the chromophores. So you can easily understand now the chromophores are those groups which shows the characteristic absorption in the UV visible range of the radiations. The next term involved in the UV visible spectroscopy is oxochrome, which is also called the color enhancing group. A saturated or the unsaturated group with the non-bonding electrons when attached to the chromophore, altering both wavelength as well as the intensity of the absorption. Mainly, it causes the shifting of the maximum radiation which is absorbed by the chromophore. So when such groups attach to the chromophore, it is responsible for the shifting of that characteristic wavelength of the radiation, or the intensity of the absorption is also enhanced. For example, we have the certain groups, OH group, NH2, and it is having with the lone pair of the electrons, we have acidic group, cyanide, chloride. So these are the groups when attached to the chromophore is responsible to cause the shifting of the radiation of the wavelength which is absorbed, as well as the intensity also increase. That's why the color enhancing group. So wavelength goes on increasing. If we talk about the visible Vibgyor, so higher wavelength, it shifts. Higher wavelength is towards red end. So towards the red end of the spectra, it causes the shifting, and that group is called the oxochrome. Understood? So it is very important when it is attached to the chromophore, it causes such shifting which can be studied out in the UV visible spectra. So after understanding the chromophore and the oxochrome, now we should understand the absorption and the intensity shifts, because the oxochrome groups are responsible for shifting of the characteristic wavelength absorbed. So let's see the different absorption and the intensity shifts found in the UV visible spectra and their causes. The first shift is bathochromic shift, which is the absorption shift, which is also called red shift. The hypsochromic shift is also the absorption shift, which is also called blue shift. The hyperchromic shift is the intensity shift, and the hypochromic shift, it's also the intensity shifts. So the two are the absorption shift, and the another two is the intensity shifts. So this is the absorption spectra we get from the UV visible spectroscopy. On the x-axis we have the maximum wavelength which is absorbed. This is the peak representing, this is the maximum wavelength which is absorbed by the sample. On the y-axis we have the intensity of the radiation which is absorbed by the sample. So this is the absorption spectra, and this is the lambda max. Now we are able to see the various shifting in this lambda max causes by the various groups responsible. Towards the right hand side here, I am saying that the bathochromic shift towards the longer wavelength. When this absorption maxima shifted towards the longer wavelength, it is known as bathochromic shift, or longer wavelength, that is red shift. That's why the bathochromic is also called red shift. So towards the higher wavelength, right hand side, the shifting causes of this lambda max, this is called bathochromic shift. If this lambda max is shifted towards the lower wavelength, that is called hypsochromic, and which is also called blue shift. So towards the left hand side, we are having lesser wavelength shifting, that is called hypsochromic shift, blue shift. So these both are the absorption shift which is causes the shifting of this lambda max. When the oxochromes are attached to the chromophore, it is mainly responsible for the bathochromic shift. the oxochromes. If oxochromes are not there, then we have the shifting hypsochromic. Then if we talk about the intensity shift, we have hyperchromic shift, which causes the intensity become higher. So when the absorption shift bathochromic occurs, the hyperchromic itself occurs. When longer wavelength shifting occurs, the intensity increases, the hyperchromic shift. The intensity increases. When the intensity of the radiation decreases, that shift is called hypochromic shift. So these both are the intensity shifts, and it is due to the when the shifting causes in the absorption, the intensity always goes on shifting. When it causes bathochromic shift, hyperchromic occur, intensity increases towards longer wavelength. And if we shift towards the lower wavelength, intensity decreases and it results into the hypochromic. So hypsochromic and hypochromic occurs together, and bathochromic and hyperchromic occurs together. So bathochromic shift is also called red shift. The absorption shifted towards the longer wavelength, as we have seen in the spectra, and it is due to the change of the solvent and the presence of the oxochrome. So these are the main causes of the bathochromic shift uh, just occurs in the spectra. So it is due to the change in the solvent which causes such shifting, and the presence of the oxochrome. As the oxochrome is present in which is attached to the chromophore, it is responsible for this shifting. So here you can have the example, that is one transition between N to pi star for the carbonyl group. This is T double bond O group, when the transitions occur with the non-bonded electrons towards the pi electrons, double bond. So these are the representing the pi electrons in between, and these are the non-bonded electrons. So this shifting causes uh, such experiences the bathochromic shift when the polarity of the solvent decreased. So when the polarity of the solvent goes on decreasing, this transition experience the bathochromic shift. So change in the solvent is responsible for the bathochromic shift, as well as presence of the oxochrome like OH we have talked about, yeah, methoxy group, methyl group. If it is there attaching to the chromophore, it is also causes the bathochromic shift. So change in the solvent, like polarity of the solvent, if it is decreased, it causes the bathochromic shift in carbonyl compounds, and the presence of the oxochrome always causes the bathochromic shift. So next one is hypsochromic shift, which is also called blue shift, because it causes the shifting towards the lower wavelength or shorter wavelength. It is also due to the change of the solvent towards high polarity. As the polarity decreases, the bathochromic shift occurs, and the polarity is increases, the hypsochromic shift occurs, or removal of the conjugation, or due to the effect of oxochrome. If oxochromes are removed, the conjugation is removed, it causes the hypsochromic shift. Understood? So aniline shows the blue shift in the acidic medium. It loses the conjugation. So aniline having the lambda max 280 nanometer, when it in the acidic medium, the electron goes on moving and the proton goes on attaching and removing the conjugation. It causes the shifting towards the low wavelength. 280 nanometer, it causes the shifting 265 nanometer. So the removal of the conjugation is also responsible for the hypsochromic shift. The hyperchromic or the intensity shift, it is due to the increase in the intensity. It is due to the presence of the oxochrome or the introduction of the oxochrome. The alkyl substitution produces the hyperchromic effect. For example, here the pyridine, it is having 257 nanometer lambda max and its intensity is 2750. And if we talk about its alkyl product, that is 2-methylpyridine. 2-methylpyridine is causing the shifting in the absorption lambda max. If you are able to see, pyridine is having 257 nanometer absorption. It is also increased to 262 nanometer. So it is causing the bathochromic shift. Understood? So as we have seen, towards longer wavelength, if the shifting occurs, it is the bathochromic shift. And here if we see the intensity wise, again there the intensity of this 257 nanometer is 2750 and 262 have the higher intensity, it is about 3560. So when it causes the bathochromic absorption shift, it causes the hyperchromic shift, that is intensity also increases. So due to the presence of the oxochrome, the intensity increases and the substitution, the alkyl substitution is also responsible for the hyperchromic shift. Then the hypochromic shift, which decrease of the intensity, it is due to the introduction of any of the group to the compound which going to alter the molecular pattern of the compound that result into the hypochromic shift. Here you can have the example, biphenyl absorption is 250 nanometer and its intensity is 19,000, whereas the 2-methyl biphenyl has an absorption 257 and its intensity decreases, that is of 10250, 10,250. That is 19,000, here 10,250. So intensity also goes on decreasing. So we can have introduction of any kind of group which alter the pattern. It is also responsible for the hypochromic shift, and generally due to the removal of the conjugation or the removal of the oxochrome. So this is all about the UV visible spectroscopy. We have seen the principle, how the transition occurs, what's the main type of the UV visible spectroscopy, and the various terms involved in the UV visible spectroscopy. In the next lecture, we are going to take the instrumentation part and the application part of the UV visible spectroscopy. Thank you and take care.